We're group 4 and we did a simulation analysis of the Auburn University LEGO Lab. My name is Hugh Smith.
Colin Babbitt-Oldu.
Hannah Thummel.
Mary Kay Barrio.
The LEGO Lab consists of 15 workstations arranged in 3 different cells. The lab produces 2 models, a speeder and an SUV. We were tasked with conducting a simulation analysis of the LEGO Lab under different operating strategies such as push and pull. And our key stakeholders are the Auburn University Industrial Systems Engineering Department as well as Tiger Motors. This is a snapshot of our model, and that's a custom-built workstation that we made in order to look like an actual workstation in the LEGO Lab. Our objectives were to develop a model capable of experimentation, such as buffer capacities, worker allocations, etc., conduct analysis of the current system, and to come up with recommendations of a new system and develop models to compare performance metrics such as time in system, number in system, work in process, throughput, and utilizations. And we created 3 different models: a mass system, which is push, and that's the system that as is right now, the lean full system using Kanban, and then another lean full system using Kanban and cross-trained workers.
Our team collected data in several phases. The LEGO Lab time studies, in which we just measured our time, how long it took us to build the model cars. A lean manufacturing course, in which we did simulations with the LEGO Lab and used that data from that. And tape measures to measure actual distances in the lab. Our assumptions are that there were no stockouts, which we observed during the process. And material handling was not a primary objective, so we assumed infinite part supply. There is 0 travel between workstations, but then for the travel between cells, those were done by team leaders, and they traveled at approximately 1.38 meters per second, which is the average speed for a human to walk. And then our processing times were normally distributed as referenced from Dr. Smith's input analysis and online sources. For the current system, it was a mass system, and there were 15 servers, each with own processing time distributions. The team leaders, like I said before, delivered parts between the cells at an average human pace. There was a button available for switching between SUV and the car. And then animation was used. We made pie charts to show the resource state, which could be either blocking, starving, process, or idle time. And then we experimented for 8 hours using OpQuest and on buffer and regular experiments. And the performance and metrics included width, time in system, number in system, throughput, etc. The buffer analysis was performed for different capacities. And this is a screenshot of the mass system. And the pie charts over here, the red is blocked, yellow means starved, and green is for processing.
Our second model was a lean system. The reason we decided to go with the lean system was because after many experiments, it really didn't affect system metrics very much. As we put the capacities to infinity, we created a huge amount of width in the system, but the throughput remained essentially the same. This is mainly due to the placement of 2 bottleneck resources. So what we did was we decided to go with a lean system in order to try to improve the performance metrics. We created a custom server object overriding the basic server logic, and we called it a Kanban server. Kanban is a principal component of lean, and it's essentially production control. So our Kanban server monitored the downstream buffer for changes in its contacts. If it reached a certain or exceeded a certain threshold, the upstream buffer would shut down until the downstream buffer had processed enough entities for it to reopen. And both of these, the amount of entities it took to shut down and to reopen, were user-selectable properties. And then on top of that, since these servers were shut down, the workers of these servers became idle. So we decided to include cross-trained workers so that these otherwise idle workers could go and assist the downstream server, which does actually happen when the lean course does its final production run and fully implements lean. Cross-trained workers are a key part of that system. Here's a screenshot of our lean system. It looks pretty similar to the mass system, but you can see that we have paths, bidirectional paths, where the station specifically between 1 and 2, 3 and 4, 6, 7, 8 and 9, 11 and 12, and 14 and 15 have cross-trained workers. The cross-trained worker only travels downstream, it does not travel back upstream. We verified the model using the animation. We also just looked at the results and they made sense. And when we first analyzed the math system, we tried an off-quest experiment which ran for over 800 scenarios, and there was not a serious difference in any of the results other than really just the width and the number of systems. This is due to the major bottleneck, which is almost double the average processing time at Station 4, and again at Station 12. So as you can see here in this table, when you have buffer capacities of 3 between each station, your throughput is very similar to if you had infinite, we used 100, but it's essentially infinite, or 0. Your average time in system obviously changes because this limits the number of entities in the system. But your production rate stays essentially the same. We've already been over this slide mostly, but the Kanban and cross-trained workers seem to be a viable solution in our minds. A lot of the ideas came just from observations in our lean course and seeing how that system improved. And in Dr. Black and Dr. Phillips' textbook, they define Kanban as controlling a predetermined level of inventory within a cell and between cells to minimize width. Downstream buffer monitoring can essentially be thought of as Kanban cards authorizing production. It's a slight modification, but essentially the same. So when we compared our systems, we compared our standard mass push system to a lean system without cross-trained workers and then the lean system with cross-trained workers. And as you can see on each of the 3 graphs, it's a stair-step improvement. Once you go from push to without cross-trained, then you go from without cross-trained to with cross-trained. It's just a steady improvement. And the percent differences in throughput, when you compare the lean system with cross-trained to the standard push model as is, you get a 23% increase in throughput, a 32% decrease in time in system, a 19% decrease in the number in system, a 24% increase in the overall utilization, 28% decrease in the summer average buffer contents, and a 23% increase in the production rate. These are very promising results, and they don't require any additional investment in the system, rather just rules that workers have to follow and a little bit of cross-training. The results make sense because, as we said before, the proportion of time the servers originally spent blocked is now utilized. You can see at almost every single station, the lean with cross-train generally has a higher utilization by a large factor. At Station 4 and at Station 12, they did not, which are the key bottleneck stations we discussed before. You can see the average buffer contents typically are lower in the lean system, mainly in the stations preceding the large bottlenecks, which again makes sense with standard manufacturing theory. So yeah, essentially what we would recommend is that the lean system be implemented. We're very proud of the results that we got, and we think they make good sense.
In conclusion, we have successfully created models that had a greater understanding of the LEGO lab and can be used for experimentation. System improvements have been discovered, and we recommend using the lean system, like you said. We recommend supporting further research and development to improve the models and get better data and try